All right, welcome back, my friends, to episode 40 of Uncertainty and Probability Theory, the Logic of Science. This is William M. Briggs. And today, I know I promised us we're going to start cause. We are. In fact, I'm going to record the lecture of cause right after I record this because it's fresh in my mind. But this subject came up in other work I was doing, and I thought it rather important not to skip. And I want you to trust your equation. I want you to trust, we proved, remember, a long time ago, we proved Bayes' theorem. We proved it was the form, the mathematical form that probability should take, using very simple English language, plain English language questions, plain whatever language you are, they're the same types of premises. We derived the mathematical form probability could take. And that just turned out to be Bayes' theorem. And as long as you trust the equations and you write down the equations the way I taught you. So today's lesson is also going to be a lesson on notation. And remember, I warned us many times, notation can be a help or a hindrance. And if you are loose in writing your equations. That's what I'm going to prove to you today. And I warned us about this many times, but it could lead you astray. And in fact, what we're going to talk about today is the whole subject is epistemology. That's what we've been doing since the beginning. Our subject is science. We're interested in science, of course, but we're interested in how we know what we know about science in particular, and that's epistemology. This, not next time, but we're going to hint about it in cause, in the first lecture of cause. The lectures of cause will be several of them because it's the most important topic that we're going to cover. Cause is going to turn out to be partly ontic, about the way things are, and it's going to be partly epistemological, about how we know about the way things are, or the uncertainty we have in the way things are. That is our entire subject with probability. Probability is epistemology, mathematical epistemology. All right. And so this came up in other work that I'm doing, and I'm having to comment on I'm going to be involved in a webinar and commenting in part on the anthropic principle and so forth. And part of it came up the problem of old knowledge, and I didn't want to bother those people listening to a long lecture on the problem of old knowledge, the so-called problem of old knowledge. And I thought I would bother you guys instead. I'm going to give you a couple of different examples. This is going to prove to you how sloppy notation, how notation where we're not writing down everything we know in our probability equations. And I told us it's fine to do that as long as we're going to be sitting down with a pen and paper and we're working out some equations, we're working out long strings of math to try to prove certain theorems and all this kind of stuff. It's absolutely fine. However you want to mark that down, it makes no difference. But when you finally move to discuss your probability equations with other people, if you don't write them down in the full form, which I'm going to remind us of, you risk forgetting what you know, or you risk the fallacy of equivocation, which is knowledge, which is premises that change throughout your equations, and you end up starting believing one thing and you end up saying something entirely different, and you miss your fallacy of equivocation. That's what this problem of old knowledge is. And there's so much ink spilled on this. This is a problem that started in 1985, I think it was, by a guy named Glymour or Glimor. I don't know how to pronounce his name. Glymour, Glymour, something like this. And I'm going to go over this so-called problem. There's all kinds of things like this that happen in Bayesian epistemology. And they all come down to the same thing, forgetting the notation. It's just a problem of notation. Nothing more. We've already proved the form Bayes takes. So whenever we come up with these paradoxes, a couple of weeks ago we did paradoxes, some paradoxes, it's got to be, where does the fallacy lie? Where does the fallacy lie? Since we proved to our satisfaction probability had to take a certain form, when people introduce difficulties about it, it has to be that a mistake was made. Mistakes are made all the time. And this one is still made, this problem of old knowledge. So let's go through this. And I want to emphasize one thing before we do this, and we're going to talk about this much later in the class, but decision is an act. Whether or not you act like something is true, like you build a device based on some theory which you believe is true, that happens all the time in science. That is an act. That is a physical act. We're going to go over this many more times. Probability, however, is just some statement about some proposition in which you're interested, and it lives between 0 and 1, depending on the evidence and its relation to the proposition. This can be a very complicated proposition. It can be multidimensional, very mathematical. This is just the sort of cartoon schematic of these things we've been doing. And that'll give you a number, whatever, p, some number in there. That's not a decision. That is a probability. If you move from that probability to decide about why then you've committed an act. And that's not probability. Decision is not probability, and we're going to learn that when we learn about so-called hypothesis testing and so forth. Okay, but it comes up in these kind of things, so I thought I would bring it. Now, the so-called problem of old knowledge. We have that some hypothesis is said to explain a known set of evidence, E, observations and so forth. This happens all the time. In physics, you know, the standard examples of certain theories, we've taken observations to show something in quantum mechanics, say, and so forth. We have a certain theory that we develop based on those observations, and we say we have a theory that explains this known evidence. No problem. That happens all the time. We could say that, we want to say, and Glymer asks, is H confirmed? How do we tell that H is confirmed or disconfirmed by E? Well, it's very simple. They didn't write it down, but it's confirmed if the hypothesis, the probability of the hypothesis, given this evidence, whatever this evidence is, whatever the hypothesis happens to be, and this is crucial here, this is going to be whatever background evidence that we have, in addition to whatever observational evidence that we have, the evidence confirms H as long as the probability of H, oops, not E, sorry, as long as the probability after observing, not after, I warned us about this many times too, and I've fallen into this bad habit of language myself. Not after. There's no, in fact, we often misuse the terms prior and posterior and so forth. These are terrible terms because it's not after. It's just whenever we consider E, whenever we condition on E, if we condition our hypothesis on E, if that probability is greater than not considering E, given this same background information, which could change, if we change this, it could absolutely be, I'll just put a Q in here for no reason, it could be that this is the case for some other background information, that other types of entirely different theories that people are considering or schemata that are not hypothesis involved in this hypothesis, different worldviews entirely. This could be the case. In this case, when we start with this K, and I'm going to use a K because this Glymer did, whatever, he used a K, and I'm going to keep with that in case you run into the literature on this kind of stuff. But in any case, once we assume E with respect to this background information, if the probability of the hypothesis increases, without considering E, why then E is confirming it. If this goes the other way, less than, well then E disconfirms it. Or if it's equal, then E is irrelevant. That's a very good question. That's a very good thing to do. Let's do that. And we're going to learn this again. This says that E, in the face of Q, of course, is irrelevant. The probability of the hypothesis is just as likely assuming E as it is not assuming E in the face of whatever this Q is. That just says that E is irrelevant. And that's going to be turning out to be a much better term than you're going to hear this term. You'll see this term all the time, independent. And the problem with this independent term is it has connotations and implications of causality, when we start talking about causality, that aren't true. And people are misled into thinking, proving or disproving certain causal beliefs about these theories and so forth. So a much better way to think about these things is irrelevant. Knowledge of E is irrelevant in the face of Q. Okay, I've said all this. Can we say that H is confirmed by E? Yes, and it doesn't matter when we observed E. We could have formed our hypothesis after seeing E. We've taken a bunch of observations. We want to know whether or not our new radio equipment is going to work, if we're going to bounce a signal off the moon and so forth, and we have a certain theory that an antenna of a certain shape is going to give us a superior signal strength or something like this. We take the information that we gather this information, and we tweak our hypothesis. There's absolutely no problem in the world of doing that. And we come to say that E now supports this hypothesis more than just whatever background information we started with. There's no time in these, unless K has explicitly mentioned time, time is not relevant to this equation. Okay, that's a key question. Now, I have to erase all this. That's pretty simple stuff anyway, I hope, for all of those who have been paying attention up to this point. Let me get rid of this. I'll keep Glymore's name there, Glimore. I beg his pardon for not learning how to pronounce it before I started this. Now, we have things like Bayes' theorem. And this is the wrong way to write it, but this is from a paper on Hausen. He is a well-known philosopher who works on Bayesian epistemology and the like. He writes this problem, he writes Bayes in this way. With regard to this so-called problem of old evidence, and I'm going to quote you some things here in this way. Now, here we come to our notation. I have told you, never write probability X just like this. No probability is unconditional. There is always going to be some condition, some premises, tacit, implicit, the language, the grammar, the definitions, all of that stuff that happens in math. It's all in there. It's all in there. Whatever the definition of X is, that's part of this. Whatever the condition is, whatever we're considering is part of calculating this probability. Now, we can leave it out when we're going to town and we're like I say, we're calculating a lot of stuff, and it's a pain in the butt to keep writing this stuff out every time. Absolutely fine. But in the end, if we write things like this, we're inviting problems. And now I'm going to prove it to you. Okay, so now this is, I'm quoting Hausen. He says, this kind of stuff, this probability of H given E and so forth, is all relativized to the individual's stock K, which is background knowledge, whatever the background knowledge we happen to be assuming, of contemporary background information. This relativation has the following unpleasant consequences, however, says Hausen. If E is known at the time of H is proposed, then E is in K. He says E is in K. If E is known at the time, if E known when H proposed. And I'm going to provide a link to this paper. So if you don't have this stuff memorized, it's going to be on the site. I'm going to write about all this stuff, so it'll be there written. If you can't quite follow this, it's going to be there. The original paper will be there, the link to it, and my explanation of all this. Anyway, he says E is in K if E is known when H is proposed. Okay. So, he says, this is Glymore's problem, Glimore. Probability E equals the probability of E given H equals 1. Then, the conclusion is the probability of H given E equals the probability of H and therefore E, the old evidence, gives no support to H. And the problem is, pause it here. I've already given you the answer, but I want you to pause it here and think about it before I tell you. Did you pause? Don't cheat. Think about it. Okay. The problem is, this is wrong. It's wrong because it's written badly. First of all, E is in K, and K is part of the background knowledge. So let me just write it out for you like this. In other words, okay, I'm gonna erase all this up here. So we keep all this. Well, I erased Bayes' theorem there, but it doesn't matter. We all memorized Bayes' theorem a long time ago, didn't we? Okay. The problem is, if E is in K, then we can write K, and I'll write K with a little subscript C to mean capital. In all these write-ups and everything, it's always given as a capital K, but I'm not going to be able to do it so good on the board. So I'm going to write a little k for L, a little small case K, and E. So that's what it means by E is in K. We have whatever background knowledge we have that's not E, little, small. I'll make it an S. How about that? No, that looks too much like a C. I'll just call it, I'll call it L. Capital K is this. That's the conclusion. Now, we wrote this by saying, well, we know that the probability H is K, given K. That's our background information that we're going to start with all this. Well, that must mean it's the probability of H given little k, capital K, little k, and E. Well, you can see the problem right there. We've already got E in here. E is part of K. That's the whole problem. And if we have, that is to say, the probability of H given E does not equal the probability of H given K, little k, and E. These are not the same. These are not the same probabilities because we've already have this in here. And we could see this quite easily. Let's look at this again. Let's look at Bayes' equation again. We can see all this. It just falls out instantly. If you write everything that you know inside the equations, what you're going to start with, in other words, we have to have that sort of, here's Bayes' theorem again, how they wrote it. And I'll write it up again like this. E given H, and a probability of H. This is the way they write it, and then I'll write it clearer here. Probability of E. That's the way that they wrote it. But we start by knowing the background K. That's what they said. Capital K, which of course is little k and E. And whatever is over here has to be over here too. So this will be little k and E. The probability of E given E is going to equal 1. And so the probability of E is just going to be this, the standard Bayes theorem. It's going to be exactly, it's going to have to also contain the background information capital K, which of course equals little k, just by consequence of Bayes' theorem, and E. So that probability has to equal 1. So this drops out. And of course, we have to bring it over here. We have that same capital K, which is little k, and E, which is E, and E is just E. So the probability is no different. There's no problem of old evidence. The probability of H given E and little k is just not the same, does not equal the probability of H given little k. Once we learn E, the probability changes unless E is irrelevant. So there's absolutely no problem. There's no problem whatsoever about old evidence. The problem came, and they even stated it, but they didn't write it out. They didn't write it out in Bayes' theorem. If they would have wrote it out in Bayes' theorem, they would have seen it was absurd. And this is still going on. People are still writing papers about this problem of old evidence, all kind of solutions. There's all kind of difficulties with Bayes. No, there's absolutely no difficulties with it whatsoever. Okay, I'll give you one more problem, and I might leave it as homework, but this one's just absurd. I got this off plato.stanford.edu. They have a very nice philosophy encyclopedia, I guess you could call it. People write a bunch of articles on all these different topics. And this particular one is the Bayesian, I'm stealing this from the Bayesian epistemology article. I'll have a link to this on the websites and so forth. And so here it is right here. This is a strange one. A person's wants to come to the, here's a septum. A person's coming to the guardian of Shangri-La. Shangri-La, I don't know how to spell any of that stuff. Anyway, the guardian of Shangri-La. And the guardian of Shangri-La tells them, I'm going to flip a coin. I'm going to flip a coin. I'll flip coin. If it's H, you'll go by the mountain path and arrive at the destination of Shangri-La. If it's tails, you'll go by the C, but I'll change your memory. So when you arrive, you'll think, mistakenly, you went by mountain. Okay. Now, this is all the words of the guardian. The words of the guardian. You, hearing these words, the person going this path, hearing it, all the evidence that they have, I'll just call it, we'll keep with K, believes it. You believe it. You believe these words. The guy flips the coin. Flips the coin, and you either, no matter what, you're going to end up in Shangri-La. So this turns out well for you. But if it's heads, you go to the mountain. You go by the mountain path. If it's tails, you go by the sea. But once you get there, the Shangri-La elders, for whatever reason, this is from a paper. All right, this is seriously discussed. Changes your memory. And you think you came by the mountain path. So So when you get there, though, they say when you get there, you're in Shangri-La. You're in Shangri-La. The evidence is you're in Shangri-La, and you're doing on the words. What's the probability you went by the mountain path? Well, the probability you went by the mountain path, truly went by the mountain path. Truly went by the mountain path, and if you're in Shangri-La and you believe the words, this is all the evidence that you have, well, that's a half. But here they introduce the wrinkle. They say, but there's no problem with this. So far we're okay. You're in Shangri-La. You remember these words. And you wanted to know, what's the probability? For whatever reason you're interested, did I really come by the mountain path or did I come by the sea? Well, you calculate this. The probability is a half. Because there's two choices, it has to be one. Just like a coin flip, you have to be in one or the other. There's no, you must decide, so the probability is a half. But then they say, well, the probability here is, they say, but the guy, the guardian gets ahead, flips the coin, gets ahead, and you go by the mountain path. But once you get there, and so the probability you're going to go by the mountain path, I guess I'm giving you the answer. You're not in Shangri-La, not in yet, but you believe W, and you see the H. The probability will be 1. And they say this probability does not equal this probability, therefore there's a problem with Bayes' theorem. Obviously, there's no problem whatsoever, because you're not in Shangri-La here. You still believe the words, that's true, and you got the H. Here, there's a contradiction in this theory. You no longer know whether or not the guy flipped ahead. because your memory has been, they don't say anything about them. For one thing, they don't say anything about whether or not they wiped out your memory of the coin flip. If you remember it's a head, well, then the probability must be 1 here too. If you knew it was a tail, well, then the probability must be 0. If you remember it's a tail. So even if they fooled with the guardians fooled with your memory, so you think you came by the sea. If you remember, if you believe the words and you remember the coin flip, the probability is no problem. There's absolutely no problem with this. The problem is they forgot to put information about what's going to happen with the coin flip. Do you remember the coin flip or don't you? That's all. That's it. It's as trivial as that. I can't stress this enough. It's as trivial as it sounds. But there's dozens and dozens of papers like this. I'm going to give you the link and you'll see. People discuss this stuff all the time because they don't write it down like this. You're in Shangri-La, you believe the words, and you remember the coin flip. And the coin flip was H or T, which is not the same thing as you're not in Shangri-La, you believe the words, and you saw it was an H or a T. They're not the same thing. Even though this one is the same. This proposition of interest is the same in both cases, but the conditioning information changed. And so therefore the probability can change. We've said that from day one. You change the information, you change the probability. That's just the way it is because nothing has a probability. There is no such thing as coming by the knowledge of truly going on the mountain path. Nothing has a probability. Probability is only with relation to the evidence you assume. So we did the paradoxes already. We've seen these paradoxes. We're going to see more when we talk about causality. All right, that's it for now. Look down below, wmbriggs.com, wmbriggs.substack.com for more information. And next time, absolutely, we're going to start causality. All right, that's it. Thanks for listening.